Today, we will be talking about imaginary numbers and where they arise from. So let's start off by looking at where they first come up and why they are important. They first appear when studying quadratic equations and their roots. Ax squared plus bx plus c is equal to 0. Quadratic equations have two roots by the fundamental theorem of algebra. This means that the roots are either real or not. So when we use the quadratic formula to solve for the two roots, we will most of the time get two real roots. But there is also the possibility that the roots are not real. When we look at whatever is inside the square root, usually called the discriminant, we notice that for the roots to be real, the discriminant has to be greater than 0 because the square root only has inputs of positive values, and if it is negative, we don't get a real value. We get an imaginary value where the square root of -1 is I. This tells us that when our quadratic equation does not have any x-intercepts, we have what are called complex roots. These roots are usually found in the complex plane. Yes, these still counts as solutions to our quadratic equation. Let's look at an example of a quadratic equation with two real roots and a quadratic equation with no real roots. The first quadratic equation with two real roots is x squared plus 4x is equal to 5. We will first subtract 5 from both sides and then solve this using the quadratic formula. This will give us x equals -4 plus or minus the square root of 16 minus 4 times -5 all over 2. This can be simplified to x equals -4 plus or minus 6 all over 2. Therefore, the two solutions are x equals 1 and x equals -5. So we see this quadratic has two real roots. Now we will look at a quadratic with two complex roots. Let's look at x squared minus 6x plus 12 equals 0. If we try to use the quadratic formula, we will get that x is equal to 6 plus or minus the square root of 36 minus 4 times 12 all over 2. Then after simplifying, we get that x is equal to 6 plus or minus the square root of -12 all over 2, which equals 3 plus or minus I times the square root of 3. So we see that imaginary numbers are spotted early on in polynomials. And this isn't a coincidence, this is normal as we go up in degree. But imaginary numbers weren't seen as important at first because they were just seen as irrelevant solutions, or no solutions to mathematicians back then, until in 1500. Mathematician Scipione dal Ferro found a solution to one type of cubics known as depressed cubics written as x cubed plus p, x is equal to q. He found the solution and on his deathbed passed it on to his student. The student in question was Antonio Fiore, who challenged a mathematician by the name of Niccolo Fontana Tartaglia to a math duel and lost because Tartaglia managed to find the solution to depressed cubics too. Another mathematician by the name of Cardano sought Tartaglia for the solution to the cubic and soon after he gave Cardano the formula. After that, Cardano was studying cubic equations and found that some cubics result in negative square roots, which is what we will dive into now. The cubic formula was found in the 1500 and this is what it looks like for the depressed cubic. Yikes, scary, huh? Well, it's not that bad. We see that it's the sum of two cube roots, and here the only thing that's different about the two cube roots is the plus and minus sign before the square root. Let's look at an example of a cubic with one real solution, x cubed plus 3x is equal to 2. If we solve this cubic using the formula, we get x is equal to the cube root of 1 plus the square root of 2, and plus the cube root of 1 minus the square root of 2. We see that we have only one real root. However, what about the other two solutions? Well, I'll leave that for you to figure out. So we see that the cubic formula works. Now let's go ahead and look at a cubic with three real roots. X cubed is equal to 15x plus 4. If we plug this into the cubic formula, we get that x is equal to the cube root of 2 plus 11i and plus the cube root of 2 minus 11i. Uh-oh, we have a complex number inside the cube root. This is the problem that Cardano faced when solving cubics using the formula. What do we do? Well, here we will convert everything into polar coordinates. This will help us get rid of the long complex cube roots. So we start by looking at 2 plus 11i. We can rewrite this as r e to the I theta, where we have to find r and theta. Let's go ahead and find r. To find r, we will plot the value of 2 plus 11i in the complex plane, which will give us this. We then form a right triangle and use the Pythagorean theorem to find r. Woohoo! We found r! Now we will find theta. It's simply the angle formed by the real axis and r. We will use the tangent function because we have our opposite and adjacent sides. This will give us tan theta is equal to 11 over 2 and solving for theta, we get tan theta is equal to arctan of 11 over 2. So, after replacing everything inside the cube root, we get all of this. This is scary. Well, let's just simplify everything and hope it isn't as scary as it is right now. Oh, look at that! Everything simplified perfectly, and now we just have 2 root times cosine of arctan 11 over 2 divided by 3. Woohoo! And after a lot of simplifying and manipulation, we see that the cosine is equal to 2 divided by root 5, which simplifies to 4. The other 2 solutions are now shown on the screen. We see that it indeed gives us all 3 solutions to the cubic. Woohoo! And they are all real, yay! So, we see that all of our work paid off. We encountered complex numbers along the way, but in the end, they vanished. This shows that imaginary numbers play a huge role in connecting algebra to higher level math. What did you think about that? We managed to get through the scary math equations and scary concepts. If you feel confident in what you learned, here are a few cubic equations you can solve. Good luck, and with that, Miku says bye-bye.